Good day, goeiedag. My name is Johan van der Spy, and I'm the head of the Department of Mechanical and Mechatronic Engineering at Stellenbosch University. I'm going to tell you a bit about the degrees that we offer, give you a bit more exciting information about what we do. So, in terms of the programs that we have at our department, you can see that we've got two degrees that we offer, bachelor degrees. The one is the Bachelor in Engineering Mechanical and Bachelor in Engineering Mechatronic. Both of those degrees are registered with the Engineering Council of South Africa, and if you've obtained those degrees, you will be able to register as a professional engineer eventually in your career. We also offer degrees in Masters in Engineering Mechanical and Masters Engineering Mechatronic, but those we will not discuss today in this presentation. That's what you'll do after you've been successful in pursuing your bachelor's degree. And then finally, we also have PhDs for those that really like Stellenbosch a lot. So we often get this question, so what's the difference? We have two degrees in our department and both are separate. So we've got a mechatronic degree and we've got a mechanical degree. So people often ask me the difference between the two. You'll see in this picture, we give you an outline of the streams that we offer in each of the degrees. And you'll see the first 2 years are sort of blanketed with a what you call purple there. That means that the two first years of these degrees are exactly the same. So if you're in a position where you can't really decide between the two, you still have 2 years to decide. And after 2 years, you can then decide whether you really want to be mechanical or mechatronic. Then after those first 2 years, you go into specializing. On the mechatronic side, you will see there's a leg that comes up on the right-hand side that's called computer systems. And that's where we train you or teach you or introduce you to the concept of developing purpose-made computers that you can use to control mechanical systems. You'll see that there are some subjects like heat transfer and vibration and noise that also come up in mechatronic engineering that we also teach in mechanical engineering. And in between, you will see that there's data science that both of the two degrees do. You'll also see, if you look at mechanical engineering, it is the traditional degree. It's quite an old degree. And you'll see right in the middle of the mechanical engineering degree, there's this one leg that we call design, or ontwerp in Afrikaans. And that is around which we focus our degree, because we believe that our engineers must all be able to do proper design of whatever they are working on. So if we want to look into a bit more detail, what does mechanical and mechatronic engineers do? What does it involve? And technically, specifically, if you consider the different, what we've done at Stellenbosch University, we've actually broken up the degrees into 5 different domains or fields. And you can see there we've got the domain of energy and the environment. We've got biomedical engineering. We've got mechatronics, automation and design. And then we've got mechanics and dynamics. And then we've got computational modeling. Now I must emphasize that these 5 domains are available both in mechanical or mechatronic engineering. So for instance, at the right-hand bottom, you'll see mechatronics. That doesn't mean that if you're a mechanical engineer, you cannot work with mechatronics. At the same time, right at the left, you'll see computational modeling. If you're a mechatronic engineer, you can still do computational modeling as well. Going into a bit more specifics, if you consider the field of energy and the environment, we're quite involved with energy, power plant engineering. That's something that we do quite a lot of. You can see on the right-hand side is a picture of what they refer to as an air-cooled condenser that's being constructed at a power plant. and you specifically use that condenser to condense the steam coming from the plant back to water that you can take back into your power plant. And what is quite unique about this system, it uses air to condense the steam, much like a car's radiator. And actually, at Stellenbosch University, we do quite a lot of research in this specific system. But as an engineer, mechanical or mechatronic engineer, you will actually come across power plant engineering quite a lot in your degree. Renewable energy. So we work quite a lot in renewable energy, and in South Africa specifically, because we've got a lot of solar energy, we've got quite a big group that focuses on solar thermal energy. So you'll see in terms of solar energy, you get what people refer to as solar photovoltaics, or just in short, solar PV. That is more of an electrical engineering discipline, where when you consider solar thermal, there's quite a lot of involvement from mechanical and then once again mechatronic engineering in that field. And this picture specifically that you're looking at is a setup for a heliostat, and a heliostat is what you use to reflect the sun's rays onto a concentrated region where you can then heat, for instance, water to make steam that you can use to run a power plant once again. Those heliostats need to be controlled and follow the sun during the day, and that is where mechatronic engineering once again comes into play. Computational modeling, and there's a lot of pretty pictures you can see here. Computational modeling, we look at aerodynamics over an aircraft, for instance, or you can see there to the left there's a picture of components, or in this case it's actually fruit being packed into a box, and you can look at the flow past that the fruit in the box. You can also analyze the strength of the box by using what we call a finite element analysis, where you look at the box itself. Instead of looking at the air, you look at the box and the structure of the box and the ability of the box to withstand certain loads on it. And you can use the same methodology to look at the strength of components that you find, for instance, in an engine or in a car or in an aircraft. Granular flow. This is also part of computational modeling, where you can now consider the flow of discrete elements and you can model, for instance, things like granules of sand, which would be quite small, or you can look at stone modeling, or actually also fruit that you can model and look at the movement in between these different granules, and for instance on a conveyor system. Then we have sound and vibration. So this is actually a picture of quite a well-known South African ship, the SA Agulhas. That's our polar research ship. And we do quite a lot of research on the ship itself, where we look at the handling of the ship and the ability of the ship to withstand slam loading, for instance, wave loading on the ship while it's cruising. And we do in-time measurements on the ship, and we monitor its conditions while it's going through the ocean. On the right bottom, you can actually see one of our researchers doing NVH measurements, noise, vibration, and harshness measurements in a car, where they specifically consider the effect of noise on the passenger in a car, and vibration on the passenger in the car. Material science. We do quite a lot of material science in mechanical and mechatronic engineering, because the components that we build are manufactured from specific materials, and we need to be able to analyze the materials. So you can go right into microscopic details and make very fine photographs of the materials. Quite interesting, to the left there's also a study that we did where we monitored the movement of a crack in a component, and we did it by a digital image correlation, where we had a camera that monitored this component and then would pick up whether the component was starting to fail and the extent to which it was starting to fail. And that you can do if you know exactly what the properties of the material is that you're working with. A very popular field that we have is biomechanics, or biomedical engineering actually, and part of the biomedical engineering is biomechanics, where you can now go and actually put sensors. You put a suit on and you have sensors on the suit, and you can monitor the movement of a body and then correlate that to mathematical models to actually see the efficiency of the movement, the direction or transfer of forces on the body, and to be able to then from there deduce the loads that's being exerted on the components of the body. We also look at, for instance, in biomedical engineering, custom implants. So you can see here, there are some pictures of a mandible reconstruction, a knee implant, and then we can also do the implant and put it into a simulator to actually look at the efficiency of that implant and the effectiveness of the implant and the ability of the implant to withstand certain loads over a long period of time, for instance. Robotics. Robotics is very popular. It's also part, once again, of mechanical and mechatronic engineering. And this is just an example of where we use robotics and actually drone technology. So this is work where we look at using a drone to calibrate the heliostats of a solar thermal power plant. So you'll recall a few slides back, I introduced you to a heliostat, and I said a heliostat's a mirror. You reflect the sun's rays are reflected onto the mirror, and then you position the mirror such that it reflects, all the mirrors reflect onto a central target. Now, for the mirror to be able to do that, it needs to be calibrated. It needs to be set very accurately. And the process of doing that calibration can take quite a lot of time. And the research that is being done is to look at the uses of drones, automated drones, to actually then automate this whole calibration process, where the drone would go and actually supply the signal to the mirror and then monitor the ability of the mirror to reflect that signal onto a target. And based on that, it can decide whether the mirror is set correctly. And this slide is just conveys an example where we apply digital twins. The fourth industrial revolution is such a popular term nowadays that's being used quite a lot by people. And what that basically entails is the use of automation in manufacturing processes or in monitoring processes or in engineering processes. And what a digital twin is just a digital representation of a physical object or a physical process. So you'll see on the left, you'll see the actual robot busy picking up parts from a conveyor, or assembly conveyor, picking up parts and putting it onto a table. And to the right, you'll see the digital representation of that same robot. Now, the advantage is you can now actually use that digital representation to monitor and actually to study specific effects. You can use that to predict what's going to happen to a system if something occurs during the manufacturing process, for instance. And that's where the advantage of this so-called machine learning or fourth industrial revolution comes in. You can use all that data that you have available to make decisions that you can then apply to the physical process. Following the completion of the third year in studies, we also offer the students, our students, an opportunity to go on an exchange with another university internationally. We have specific agreements with universities in Europe and in the United States. So the idea is that if you've completed your third year, you can actually take a break in your studies and spend a year with one of these institutions internationally. Unfortunately, the cost for this opportunity will be for your own account, but we do allow you to take that break in your studies. Then, in terms of admission and inquiries, if you have any questions, you're most welcome to visit our website at www.computational.co.za. www.mecheng.sun.ac.za, and you're also welcome to just send an email to general inquiries at mmchair@sun.ac.za. And I think the final message I want to leave you with is that mechanical engineering and mechatronic engineering are such wide and diverse fields that just showing you with 20 slides what we do is not even going to be enough. But I do hope that the few slides that I showed you was actually enough to make you excited about the prospect and the possibility of coming to study with us. Thank you.